Welcome to The Explainer. We're tackling something pretty wild today. We're taking the dense and honestly often intimidating math of probability and translating it into a clear, intuitive journey. We're literally looking at the building blocks of chaos. Whether you're trying to predict the stock market or wrap your head around crazy weather patterns, if you've ever wondered how mathematicians actually make sense of totally unpredictable phenomena, you are exactly in the right place. Here is our game plan for today. We've got 5 logical steps to totally demystify this. We'll kick things off with the rules of randomness, move into visualizing random variables, figure out summarizing the chaos, dive into when variables interact, and finally, we'll unlock this incredible concept called the characteristic function. Let's jump right in. All right, part 1, the rules of randomness, defining the unpredictable. So let's start with a big fundamental question. Can we actually predict the unpredictable? Well, strictly speaking, no. But in math, we measure unpredictability by observing it. Think about it like this. If you repeat an experiment n number of times, and a specific event happens m times, the ratio of m over n gives you the frequency. And as n gets bigger and bigger, approaching infinity, that ratio literally becomes our probability. We are actively measuring the chaos. Which brings us to the absolute star of the show today, the random variable. It's not just some rogue, lawless number. It's a mathematical quantity whose specific value is unpredictable, sure, but its overall realizations are actually governed by a very strict probability law, which we call a distribution. Now, before we start mapping things out, we've got to lay down the ground rules these variables play by. First off, probabilities. They are perfectly locked between 0 and 1, always. When events overlap, we use joint probability to measure them together. If you need to know the odds of an event happening, knowing another one already did, Bayes' law steps in for those conditional relationships. And of course, if 2 events have 0 influence on each other whatsoever, they're independent events. Those are the rules of the game. Moving on to section 2, visualizing random variables, the shapes of chaos. So, how in the world do we actually visualize these invisible probabilities? We start with the cumulative distribution function, or CDF for short. Think of this as a running score. It tells us the probability that our variable is less than or equal to a specific value. And because it's a running total, it's an always increasing function. It starts all the way down at exactly 0 and slowly builds its way up to exactly 1. To really put this into perspective, let's look at the 2 main flavors of variables. First, you've got discrete random variables. These only take on specific, exact values. If you graph its CDF, it looks like a staircase, literally taking steps up at those exact values. Now contrast that with continuous random variables. These can take any value within an interval. So its CDF isn't a staircase, it's a beautifully smooth, unbroken curve climbing its way from 0 to 1. Okay, let's take it a step further. If you take the calculus derivative of that cumulative distribution function, you get what's called the probability density function, or the PDF. Now, for those discrete, staircase-like variables we just talked about, the PDF doesn't look like a curve at all. It looks like a series of exact spikes, a structure mathematicians actually call a Dirac network. Every single spike represents the exact probability at that specific, finite point. But what about our continuous variables? Well, since they can take literally any value, the probability isn't a single isolated spike. Instead, it's represented by the area tucked underneath a smooth, flowing curve between 2 given points. And the total area under that entire curve, it is always exactly 1. It's a brilliant way to visualize exactly where a continuous random variable is most likely to land. Section 3. Summarizing the chaos. Statistical moments. Let's be real, sometimes you just don't want to analyze an entire, complicated graph. You just want the quick summary of a variable's personality. We get that using statistical moments. The first order moment is the expected value. You can think of this as the absolute center of gravity for our probability. It's the statistical average. Then we have the central moment of the second order, which is the variance. If the expected value is the center, the variance tells you how wild and spread out our variable gets around that center. Here's the catch with variance, though. It's measured in squared units, which is kind of hard to wrap your head around. So to bring things back down to reality, back into the exact same units as our original variable, we just take the square root of that variance. Bam! That gives us the standard deviation, arguably the most famous way to measure statistical spread. All right, section 4, when variables interact. Bidimensional variables. Things get really interesting when variables start crossing paths. Bring together variable x and variable y, and you've got a bidimensional random variable. If both of those are discrete, we can map out every single possible pair and their joint probabilities using a mathematical matrix. It perfectly captures all those simultaneous likelihoods in one grid. But hey, what if you're looking at this massive joint distribution and you really only care about one of the variables? That's where marginal probabilities come in. You can basically isolate just the probability of x or just y from the rest of the pack. Or if you want to know how one variable's behavior directly impacts the other, you use conditional probability. The joint distribution holds all the secrets, but these tools let you extract exactly what you need. To actually put a hard number on how these two variables interact, we pull out three main tools. First up, statistical correlation. That's the second-order moment of the two variables working together. Then there's covariance, which tracks the spread of both variables around their respective centers. And finally, the correlation coefficient, which is basically just the covariance normalized by both of their standard deviations. And all of this leads to a surprisingly simple, intuitive conclusion. That correlation coefficient, represented by the Greek letter rho, measures resemblance. If rho is 0, absolutely uncorrelated, no linear relationship whatsoever. But if rho hits exactly 1, they are completely, totally correlated, moving together in lockstep. And that brings us to our final stop. Section 5, the characteristic function, the ultimate DNA. Now, I know the characteristic function sounds incredibly intimidating, but conceptually, it is just beautiful. Practically speaking, it's the inverse Fourier transform of our probability density function. Think of it as a way to mathematically reverse engineer the variable to find its ultimate blueprint. It is the master DNA of our random variable. So why do we care so much about this mathematical DNA? Because it literally contains everything. If you evaluate this function at 0, it equals exactly 1. But its true superpower lies in its derivatives. Just by taking the derivatives of this single, elegant function and evaluating them at 0, you instantly unlock all those statistical moments we talked about earlier. The expected value, the variance, the whole shebang. It's basically a mathematical skeleton key. Which leaves us with this final thought for today. We've just taken random variables all the way from pure abstract chaos to structured curves, and finally down to a single functioning strand of mathematical DNA. So, if the characteristic function holds the exact DNA to decode basic probability, what other massively unpredictable systems out there in our universe are just waiting for the right mathematical lens to be understood? Thank you for joining me on this explainer, and keep questioning the chaos here.